So today's lesson, lesson 31, circuit components. We will learn about some of the common components in circuits. That's going to be the first main goal. I guess the second part after we've learned about that is I want to start to journey through the different types of circuits. Because I'm teaching you guys, because it's year 11, I actually have the luxury of a little bit more time to go through this. I teach this same topic to year 10 students in engineering maths, and it's usually a really quick run through everything. But because I get to teach year 11s, I get to slow down a bit, make sure that you really understand what's going on here before I go too far ahead. Let's look back at what we did last time. Last time we looked at two rules, the Kirchhoff's rules for current and voltage. The first rule being the current in is the same as the current out, which means that if I've got 20 amps and 30 amps going in, I have to have 50 amps going out. That's really useful when you have circuits where you've got something like 50 amps going in here, you've got 20 going down, 10 going across. So we can then work out, well, therefore, 20 plus 10 is 30, there must be 20 going up. That 20 goes up and comes down here. So at the end of the day, if I got 10, 6 going down, I'm going to have 4 going across. That 4 and that 20 is going to meet to give 24 amps here. And so it actually is very useful just to be able to combine amps and just work out what they would be in a circuit. I always like comparing this idea to this idea, because a lot of students go away and they think, well, we've learned this great rule, but it's only for wires that look like this. Whereas obviously the reason we show you that is so that you can apply it. Because if I gave you this and I said this is 20 and this is 4, you guys could easily figure out this is 24. But I want to show you guys in an actual circuit. All right, after we did that, the second law that we learnt from Kirchhoff was essentially about voltage, which is what we just talked about in the leading up into today's lesson. In any closed loop, the EMF, the voltage drops, is the sum of the voltage drops. They must be the same. So that means if we've got a closed loop, that must be 20 volts. For a closed loop, these two together must be 20 volts. So it's going to be 10. That's going to be 10. In this one, we've got one closed loop, two closed loops. So this closed loop is going to be minus 20. This one's going to be minus 20. Shared amongst each of those is minus 10. The reason that I know that it's the same voltage for both of those is because they're the same size resistor. So, and then I set these, and I put these questions on the Google Classroom if you haven't seen. So I'm hoping most people have done those. If you haven't done those, you need to get them done before tomorrow, because tomorrow we're going to move on to the next sort of section 4.3. So, and tomorrow's going to be a big lesson. We've got a fair bit to go through. I'm going to try and tackle all the parallel circuits and maybe as well short circuits as well, but we'll try and do that all tomorrow. So just be prepared for a big one. Today's going to be relatively, hopefully short, but we'll see. This is straight out of your textbook. I'm not going to lie. I'm not going to say that I invented it. I wanted to show you guys this. These are all the components that we are probably going to be using this this topic. So I wanted to outline a couple of them just so that we're clear. Firstly, we've got essentially the connection between conductors is usually drawn as wires. I guess that's what we're trying to say is, and when you draw a wire in an electric circuit, just so that you know, you don't draw a curvy line to a battery back to a light bulb or so on. The reason is that even though the wire that you use, if you were doing this as an actual experiment, the wire that you use might be curvy, because what we're doing is we're trying to make this as clear as possible. In circuit diagrams, we will be drawing straight lines, even though the wires themselves in real life are not straight. Those wires, if they're not connected, then what you would do is you need to give some sort of signal that they're not connected. The best way to give a signal that they're not connected is I prefer this one down here. And let's just say that we want to make sure that we know that maybe there's another wire here, but this wire is not connected to this one. So you just draw a little loop over like that. And that's how you would draw a not connected symbol. They suggest that if they are connected, that you do a little black box between them like this. I'm going to let you guys know that that's not always the convention. Sometimes they just draw, like if they're connected, they'll just draw them as a line crossing each other, which is sort of what they've said is, oh, they're not connected. But I'm just going to let you know, that's why I prefer using this one, because that definitely says they're not connected. Earth is just a line that looks like this. Earth is essentially, remember we've talked about Earth is if you've got a charge, that charge wants to get to the ground. The reason is that if you've got a charged particle, if you've got a charged rod, that rod is going to want to, the electrons are going to want to get out of that rod and spread out through the ground because there is so much space that they can go. That means is that sometimes some electrical devices have an earth, just in case there's a lot of charge they need to get rid of at once. We're not going to use that one very often, but it's just one there. The battery symbol is the next one. And then after that, we've got a variable power supply, which is usually when you've got an arrow to indicate there's lots of them. To be honest with you, this is a little bit wrong. This is not actually a battery. This is a cell. A cell is one battery, is like one single unit of a battery. In order to have a battery, you need to have more than one of these. But it doesn't matter too much. Now, resistors, we're going to use resistors as just blocks like this. You could also use a resistor as a symbol having a zigzag like this, which I'm actually very confused why they haven't included in this table, because it is another way that you can use a resistor. After that, though, there are different types of resistors. Variable resistors have an arrow on them. Notice how variable power supply, arrow. Variable resistor, arrow. So it's sort of the same sort of thing showing up here. Resistor with sliding contact. So this is a different type of variable resistor. This one allows you to change the resistance by, I think you got 2 wires to change the resistance, but I'm not too sure. Semiconducting diodes. So we've got some diodes here. We've got a switch, we've got a button. Volt and amp meters. Now we've talked about these already. Voltmeters measure voltage. Amp meters measure amps, and that's why we use them. Incandescent lamps. I've already used a picture of an incandescent lamp over here. You can use either of those two symbols. I sometimes interchange between both of them. I think one of them is American and one of them is like European, but it doesn't matter too much. Light depending resistor and a light thermistor looks like this. So which ones do we really need to pay attention to? In all honesty, well, most of these we can ignore. The ones that we really need to care about, of course, are battery. We need to care about resistor. We'll need to care about diodes, these two here, and probably thermistor is going to be pretty important too. But a lot of these we can just sort of ignore, but it's good to know that they're there. And it's good to know that this is in your book, so you can refer to it. If you ever see a symbol, you're like, what the heck is that symbol? I've never seen it before. Questions? Questions is usually just an excuse for me to get some coffee, because otherwise I'm just going to be talking the whole time. Let's go have a look at a cell or a battery. I wanted to show you guys this, and I show this to all of my classes that I teach this just so that they're clear. In a cell or a battery, you've got two sides. One of these sides is positive, one of these sides is negative. And the trick is to know which one's which. Can someone tell me, maybe someone that I taught in the past, which side's positive and which side's negative? Oh, someone in chat said something. Whoop. Let's go have a look. And come up. Left is positive. Thank you very much, Kelvin. You are correct. Left is positive. Now, it doesn't matter, obviously, the reason that left is positive, and it does matter which side is positive based on, like, because if I drew this like that, then obviously left wouldn't be positive anymore. But there is a reason. The reason why it's important for us to know which side's positive and which side's negative is if we then need to then draw the current, so the current is going this way, we need to know which side's the positive because the current comes away from the positive. So how do I memorize which side's positive and which side's negative? It's up to you. You can come up with your own memory technique, but I use this one here. If this is a long stick, imagine that this is a long stick, right? Well, then you could technically really break that stick. And if you broke that stick into two pieces, because it's long and thin, you can snap that. You could take those two pieces and you could then put one piece over the other piece to get a positive sign. And I'm like, okay, that makes sense. That's positive. What about the other one? Well, the other one, if you took that big long stick, that small thick stick, you tried to break that, you wouldn't be able to break that. So because you can't break it, well, the only thing we can do is turn that stick onto its side, makes a negative sign. So that means that this side is negative, and that's how I've memorized it. You guys might come up with your own memory technique. It might be, if it's long and thin, it's positive. If it's small and thick, it's negative. You might be like bad. You might think positive to good things and negative to bad things. It's up to you. It doesn't matter as long as you can look at the circuit and draw the current in because you know which way it is. But that's my memory technique, and hopefully that helps someone out there. One last thing about voltage drops before we start to look at circuits in general. Although there is an internal resistance in the wire, so the wires all have internal resistance, and there is a resistance in the battery, we assume that this resistance is 0. Okay, unless we have to calculate the voltage, the resistance in the battery, we're just going to assume that the voltage through wires is 0. Now this isn't obviously correct. If you leave a circuit running for long enough, even it will get hot. Any circuit left for long enough will get hot, just because the wires will lose some resistance in them. And when the wires lose resistance, well, when there's voltage drops in wires, the wires will get hot. But the voltage drop through a wire is already very, very small because copper wires are really, really good conductors. So there's not much voltage drop. So we're just going to assume there's 0. Trust me, it's going to make our lives a lot easier down the road. That means that all the voltage that is dropped in a circuit will only get dropped over resistors and other components like diodes and so on and so forth. So that's the only thing we're looking at. What we're doing is we're simplifying our circuits here. We can, and the reason we do this is not because I'm trying to dumb you guys down, but I'm trying to get you guys a grounding in what we're doing. And then as time goes on, we can make them more complex. That's what we usually do, is we start simple and make it more complex. How do you calculate how much voltage drop is over each resistor? Well, that's why we're using Ohm's law. It's also why we're learning Kirchhoff's law as well, because both of these laws together will help us find out how much voltage gets dropped. Really quickly, I pulled this picture out from somewhere else. I like this picture because it's just got this idea of, it's an analogy of a battery. It's a pump. The battery acts as a pump which transfers potential energy to electrons. The electrons will lose energy as they fall down through components in the circuit. So you can see this pump over here is a battery. It's like, essentially the pump is like an escalator that pulls the electrons up, giving them potential. This potential is this height, and then it will lose that potential as it slides down these ramps, and those ramps are got to do with different parts in the circuit, and they will lose energy as they go down different parts of the circuit, so eventually they get to the bottom where they have 0 voltage. It's just another idea, and this part here could be a wire. We assume that it's not going to lose any voltage through a wire. So because we assume it's not going to lose any voltage through a wire because, again, the resistance is treated as 0. Now, this is the big one that I wanted to get to most of this lesson, is this idea here. Oh, not this idea, but we'll get to it in a sec. Sorry, big drum roll for nothing. Series circuit. What is a series circuit? We've been talking about it a fair bit. A series circuit is one way of setting up a circuit is to in series. Okay, one way of setting up a circuit is to in series. Okay. What is a series? Current only has one path to flow through, and voltage drops are calculated by Ohm's law, like I just said before. If we grab a look at this battery, the voltage only has one path that it can travel through. One loop, as we would say in Kirchhoff's rule. Same idea here for the same idea here we would say for this circuit here. It's only got one loop. It's called a series circuit because essentially it's if you think about a book series or a television series, you will watch the first episode, then the second episode, then the third episode, and the fourth episode. You read the first book, the second book, the third book, and the fourth book. A series has an order to it: first, second, third, fourth. And that's because, and this one will have an order to it as well: first resistor, second resistor, third resistor. And the reason there's an order to it is because those electrons can't go wherever they want. They can't go through the first resistor and then through the third resistor. They have to go 1, then 2, then 3. That's why we refer to it as a series. Series circuits are pretty much series circuits are a pretty easy way to sort of deal with circuits. I find that they're the easier one out of the two. We will talk about two this week: series and parallel circuits. And we can just base off all our information that we know here. We're going to talk about a little bit about what the current's doing in the resistance in a circuit, in one of these series circuits, in a second. But I really want to address something. The first thing I want to address is I want to look at this circuit for a second. Okay. Now, the reason I want to look at this circuit is because I've done this, I've taught this so many times now, and every time I teach this, I walk away and I'm really pleased that students won't make this mistake. And they still make this same mistake every single time I teach it. And I've decided to spend some time really addressing it. These two resistors are exactly the same. They're both 10 ohms. The current comes out of the positive side, goes into the negative. So the current is going to go this way through the circuit. And I ask students, and ask them this, and I say, which of these will have the greater voltage drop? And some students will always say this one will have more than this one. If I say which of these, if I said these were both not resistors, if I said these were both light bulbs instead, I say which of these light bulbs would be brighter, students always say the one on the right. They said this one's going to be brighter. And it's taken me a long time to figure out why students think that. And my understanding of why students think that this is the case is because what they do is they say this. Okay, if we were to imagine this as instead of the current moving through the circuit, what if we were to imagine it as, well, I guess this is how I think students think, all right? So I'm not sure if this is how you actually have students and why the students make this mistake. This is my opinion. I think students think of the current as little packets of electrons, or perhaps like, imagine that instead we've got a person. That person's at the left and wants to get to the goal at the right. That's the end, that's the battery. It wants to get back around to the battery. So how does it do that? Well, it says, well, I've got 10 volts. And I think people then start to imagine that they're a runner. They start to imagine if they're running through the circuit. And they go to themselves, okay, so if I'm in a circuit, right, and I'm running from the positive side, I've got lots and lots of energy. And I'm going to use a lot of that energy at the start to get over that first resistor, because it's going to be, I'm going to lose some energy going over that first resistor. But after I go over that first resistor, I'm going to be really tired. So I guess I'm going to go a bit slower to go over the second resistor. And then that's how they then say, well, therefore that's going to lose 3 volts. Let's look at this. Has the student got anything right at all? The first thing that the students got right is that at least they've said, I'm going to use 10 volts and 10 volts gets lost. The problem is that 7 volts gets dropped over the first resistor and 3 volts gets dropped over the second resistor. Now, if this was the case, the first resistor would have a greater voltage drop. It would be brighter if it was a light bulb. The problem is that this is not how the system works. That's just not how it works at all. And that's why I think people make this mistake. They assume that, oh, it's current in a circuit is like a little man running through the circuit. You can, at the start, when you're running a race, and I guess people are thinking about when they were doing cross country, maybe when they were in primary school, like, the first part of the race, that's really, you lose a lot of energy. Whereas at the end, you have barely any energy left. So therefore it makes sense that you won't use as much energy. This is wrong. And I think the main reason that I think this is wrong, and this is how I usually draw people that I want to draw your attention to, you only needed 3 volts to get over this circuit. You only needed 3 volts to get through this resistor. Now, if you only needed 3 volts to get through this resistor, then what that tells me is that that means you're overexerting yourself on the first one, right? Electrons are lazy. Electrons don't want to do any work at all. So if they can just get away with going through 3 volts through a resistor, they're going to go through with 3 volts. So let's grab a look at a different scenario. Down the bottom right, this guy, he's going to go through the circuit. He's going to use 6 volts instead. He's going to use 3 volts to get through the first one and 3 volts to get through the second one. And that makes a lot more sense. That would work. The reason I can say this would work is because both of these are the same size resistor. So therefore, they have the same voltage drop. They got away with dropping just 3 volts. And because they all, both of them drop 3 volts, no energy is being wasted. The top one, energy is being wasted. There's more energy being wasted at the top one. So therefore, in this bottom one, no energy is being wasted. So I guess I write down, this uses the least amount of voltage. This uses the least amount of energy to ensure that it reaches the end. Now, that's pretty much answered our question here. But I guess, oh, hold on. Sorry, guys. The guy at the top is complaining about something. Okay, well, can he use 10 volts? I mean, technically he can use 10 volts, right? I'll show you how. So even though he's got 10 volts, he's got excess voltage than he actually needs. What's going to happen in this circuit? Well, the difference is that it's still going to go through both resistors. And as it goes through both resistors, it's going to drop 5 volts. Now, if we compare the dropping of 5 volts to the dropping of 3 volts, you've got a higher voltage drop. But if you've got a higher voltage drop, but the same resistance, that means the current is going to be a lot higher. And that's why in this example, I had the guy running really, really quickly compared to the last one where the guy, he didn't run slowly, but he wasn't, pardon me, he didn't run slowly, but yeah, he's dropping 3 volts at either of those resistors. So that means his current, even let's just pretend his resistance was, if we pretend the resistance was 10, okay, then that means it's going 0.3 amps. Whereas in this one, if the resistance is again 10, now the current is not 0.3, it's actually 0.5. He actually can move through those faster. So the idea is that if you've got the same level of resistance, you want to make sure that you're dropping the same voltage so that you can go through these resistors at the same speed. Let me show you a different way that you might be able to think about this. It uses more energy than it's needed per jump, but it does it faster. Now, if you had less than 6 volts, you still probably could get through the circuit. It's just it's going to take the electrons even more time. But the idea I want you to understand for this circuit is not that it's not the amount of like voltage versus current. It's not the Ohm's law I really want you to focus on. It's that the energy needs to be split equally amongst all resistors in order to make sure that no energy is being wasted. If energy is being wasted, then it's not going to work. All right, let me show you. Hold on, this guy. Okay, all right. I'm going to try and click on him and get it. Come back here. No, oh, he's gone. Whatever. He's gone. Doesn't matter. I want to show you another way you might think about this. I want to look at this from a different perspective now, current, because we've been talking about this current for a little bit. Let's pretend that we've made that mistake, right? We said that this is going to lose 7 volts and this one's going to lose 3 volts. So this is wrong. I'm going to make sure that you guys understand that I'm doing this wrong. But I want to look at something. For this first resistor, if this is V equals IR, then V divided by R, that's going to give me the current. So the voltage drop is 7 volts. 7 volts is going to get dropped. And the resistance is 10 ohms, which means the current is 0.7 amps. So if I look here, I've got at this point 0.7 amps. Okay, now if I look at this Y here, this bar here is going to drop 3 volts. Now, this is if I do the same formula, okay, the same formula is going to be 3 divided by 10 equals 0.3 amps. Okay, but now I want you guys to remember Kirchhoff's rule. I in must equal I out. What that means is if I have this situation happening, I have more current moving here than I have here. That means that as this current has to slow down at this point here for some unknown reason. And it has to slow down, and yeah, because it's slowing down, you might say, well, therefore there's going to be a bunch of extra electrons, so therefore it's not going to drop as much, it's going to drop more voltage. It's just, this doesn't work because it fails Kirchhoff's rule. You can't get, like, essentially you're saying the stream is going to go from really big stream of electrons to a very small, so a very big water stream to a very small water stream without there being any real extra resistance to do this. So that's another reason why I could look at this and say, well, that doesn't work. If instead, right? If instead, oh shit, I'm about to run out of time. So if instead we were to look at this and say, well, let's try and do this properly this time. If this was to drop 5 volts and this was to drop 5 volts, then that would mean that the current V over R equals I, the current's going to be 10 divided by 5, which is going to be 2 amps. I've got that wrong, sorry. It's going to be 10 divided by 10. Right? No. God damn. 5 volts gets dropped over here. 10 ohms is going to be 0.5 amps. And this one is going to be 0.5 amps, which means that the voltage going in is the same as the voltage coming out. The current going in is the same as the current going out. So it passes this law. And that's pretty important here. So I guess that's pretty much it for the time. I wanted to quickly give you guys, this is the homework that I want you to do. Okay, and I will put this up on the classroom as well. What I would like you to write down is, why do people have this misconception about voltage drops? Why do they have this misconception that the first resistor, even if it's the same, will drop more voltage than the second resistor? And then I want you to explain how it actually works in your own words. So I've given you guys 2 ways to understand this. The first way, using the idea that energy shouldn't be wasted by one resistor and the other one. And the second way that I gave you guys to understand this was that if you were to, imbalance the circuit, then the current wouldn't work. You'd have more current in one section than another section. So there's 2 ways you can understand this idea. Choose one of them and explain it. I want you to do this in your own words. I might even make this a question on Google Classroom so that you guys can answer it there as well. So if you want to write down a draft on your books now or later, and then maybe type it up onto Google Classroom, just so I can see how many of you guys are actually walking away being like, oh, okay, cool, I understand that now. And how many of you guys are like, whoa, okay, like I still assume that the first resistor, because it's first in the line, is going to lose more voltage than the second resistor. And yeah, just if you still think that a circuit is like little men running around dropping off voltage, you need to stop thinking about that and move to an idea of a stream of water that's pushing its way through rocks. That's the best way to get the correct answers. Anyway, guys, I've run out of time. I will see you guys, and girls, of course, sorry, tomorrow. Make sure you've done the attendance question. Yeah,